All right, thank you very much for attending my talk on the weird and wonderful world of exoplanet data. So today I'm going to be talking about exoplanet transit data and the many interesting signals that you can acquire simply from the active taking transit data, as well as the vast variety of exoplanets that exist in our universe, and how you can take exoplanet transit data as well. I would like to start with a brief history of exoplanet detection up into the modern day, just to set the groundwork for uh, how modern exoplanet science came to be. Um, Given how young our field is, I've got a question for you all. Either unmute yourselves or type in chat. What year was the first ever claimed exoplanet detection that was published in a paper? Real or false? First
Yes,
claimed exoplanet detection. Go ahead.
that is a difficult question. That's, that,
If you had to guess,
I'll guess 1950.
1950. All right, we've got one guess. So yeah, actually, the first claimed exoplanet publication detection that I could find was as early as 1855. I found a paper by William Stephen Jacob from the East India Company's Madras Observatory, which reported that there was potentially a planet around 70 Ophiuchi, which is a binary star system. Basically, the paper used astrometry to try and track the movements of the two stars in the system and tried to claim that there was a third body that was unseen, could have been a planet that was affecting the orbits of these two stars in a way that couldn't just be explained otherwise. This unfortunately turned out to be a false detection, but this was an interesting paper nonetheless. The instruments that existed during this time period were simply not precise enough to do this kind of work yet. But it's really interesting to me how early they were thinking about all of this. For for reference, Neptune was discovered 9 years before this paper was published in 1846 via Uranus's orbital perturbations. So I kind of like to think that these like everyone is just on the orbital perturbations hype train. Everyone is trying to use astrometry and tracking celestial bodies to find unknown objects. It would be a long time before modern exoplanet observations would begin to take place. I have the first kind of exoplanet detection here from 1988 around the star Gamma Cephei using the radial velocity method. Though this paper was published in 1988, it was eventually retracted by some of the authors, by Walker et al. In 1992, because the signal was not strong enough to give us a like confirmed, unambiguous detection. But there is a planet around this system. It was confirmed in 2003 that this was a real detection. It just wasn't precise enough to be published. It wasn't strong enough. The first exoplanet that stood its ground around a dead star was made in 1992. The first exoplanets that were ever discovered, truly discovered, were around a pulsar, PSR B1257 plus 12. The method was pulsar timing variations, and the paper discovered two or more planetary bodies. And around a main sequence star, the first detection was made in 1995 around 51 Peg. The planet was 51 Peg B. This was also radial velocity. So basically, we have a much more defined and unambiguous sine wave that indicates a detection. This was the first ever hot Jupiter exoplanet ever discovered, and this paper won the 2019 Nobel Prize in Physics for its discovery. Meanwhile, the first transit observation was made in 1999. Basically, this planet around the star HD 209458 had previously been observed and a planet was previously found via radial velocity, but they were able to use the transit method on this same system to confirm the RV measurements. And there are many benefits to be had by observing something via both RV and transit. So this paper, Charbonneau et al. 1999, sort of laid the groundwork for future transit observations to come. As of today, or as of yesterday, I should say, this is when I got these plots. As of August 14th, 2025, there are nearly 6,000 confirmed planets, confirmed exoplanets to date. We're not quite there yet, but I'm counting down the days. We're very close. Basically, on the left, we have planet radius versus orbital period for all planets with a known radius. And on the right, we have planet mass versus orbital period for every planet with a known mass. We have made great strides over the past few decades, over which exoplanet observations have been being made. All right, so part two, what can go wrong? I'm mostly going to be going over transit data in this talk, since that is what I work with. There are many other methods that you can use to measure exoplanets, such as radial velocity, direct imaging, and many, many more. But I will be going over transit observations today. And I'm going to go over the many silly quirks, the many silly things that transit observations can bring to your eyes. So what can go wrong? Why aren't exoplanet transits these perfect lines with perfect parabolas in them? Well, the first hurdle that a lot of people taking transit data have to contend with is that stars are not perfectly uniform spheres of light in the sky. They may be point sources to us, but they are not perfectly uniform as far as light goes across space and across time. They're not perfectly smooth, and this can introduce stellar variability even in calm stars. This needs to be corrected for if you are, for example, modeling your transit. This data that I have for you here is data from HAT P11b. It is a relatively calm star. It doesn't have super frequent solar flares or anything. And even then, you can see that the baseline is rather wobbly. And additionally, you can have features such as sunspots in your data. Again, stars to exoplanet scientists are point sources. We can't really image a sunspot on a faraway star in the same way that you can image a sunspot on the sun. However, we know that sunspots or star spots on other stars exist, partly because we can see them in transit data. In transit data, a sunspot can appear as a sort of blip in flux in your otherwise perfectly stable and normal transit. And when I first looked at data with a sunspot in it, I was really confused. Like, I couldn't really wrap my head around why, like, oh, it's a dark spot. Why would it cause like a rise in brightness? I couldn't really wrap my head around that at first. So the best way that I can kind of explain it would be a diagram. If you're looking at a sunspot, if you're looking at a system with a star that has a sunspot, let's look at the diagram on the left. You have a star, and you have your planet that is transiting over your star, and you also have a dark sunspot that is unobstructed by the planet itself. And then over the course of its transit, your planet covers up the sunspot. So basically, functionally, what you're looking at in the diagram on the right is only your star and your planet with the sunspot obstructed. So the reasoning being, the diagram on the left is going to be, in practice, darker than the diagram on the right, because functionally the sunspot is covered by something else and is functionally not there anymore, quote unquote, which is why you get like this blip in brightness. It's because the flux in your transit measurements is relative. So that's kind of why it looks like that. And And sunspots are very, very interesting for monitoring things like the rotation rate of your star, because one of the ways that you can be sure something is a sunspot and not just like some fluke of your data is if it shows up again in future transits. What I have before you right now is transit data where the transit itself has been modeled out and you're left with only the residual data. And in this data, you can see some star spots that sort of linger even after multiple times where the planet has gone around multiple times. And you can see that the sunspot moves because the star is rotating and time has passed. Um, so yeah, that is sunspots in data. Another very fun thing is solar flares. Solar flares are not really the mild little hills that sunspots can create. They are much more like jagged spikes. Generally, solar flares will have this sort of geometry where they shoot up immediately and then kind of gradually go down, but the entire solar flare generally lasts very quickly. And it's important to note that some stars are much more active and prone to solar flare temper tantrums than others. For example, many M dwarf stars, though M dwarf stars are very convenient to measure via transit because they are small and transit observations favor small stars and larger planets. Um, M dwarves are very notoriously busy. They're very notoriously anxiously flaring off solar flares. Uh, they're very angry stars. It makes them difficult to measure. I have a colleague who is working on an M dwarf star right now, and she just needed the actual star itself to behave for like 8 hours while they were taking the data. And at one point, she finally thought that she had gotten good enough data. But it turns out that there was, after taking the residual, after modeling the transit, there was a solar flare in egress that was hidden. So you always need to model your transit. Oops. Um, so yeah, these are pesky little things, especially if you're trying to model something. All right, I've got kind of maybe another interactive part here. We're going to go over, for these next few slides, we're going to go over ground-based versus space-based measurements. I have before you some labeled transits. Some of them are ground-based and others are either Hubble or Spitzer, so space-based. They're labeled in the bottom right corners of each plot. If anyone would like to tell me the differences between these two plots, or what you notice. What do you notice about these different plots, the differences between the ground and space-based data? Either unmute yourselves or put it in chat. I'm going to give you a bit of time to think. Yes, Jerry, hello.
I'd say the space-based ones seem to have less distortion because there's no atmosphere.
Yes, so basically, and I'll go over this in my next slide as well. So the biggest thing is that on the ground, you have to contend with the atmosphere, which is going to refract your light. It's going to add a lot of white noise. And there's no air in space, so space-based data does not have this problem generally. Anything else? That was the biggest thing. It's okay if no one else has any other observations.
Well, that one that you have, Rabus et al. 2009 has a little lump at the bottom.
Yes, it does have a little lump at the bottom. What is that lump?
Boy.
Sunspot.
It is a sunspot, yes. If you have a better signal to noise ratio, and if you're looking in the correct wavelengths to find sunspots, it's better to find sunspots that way. Finding, especially if you're looking for smaller signals, like sunspots or maybe smaller planets or smaller transits, you're really gonna have to like, if you're using noisy data, you're gonna have to really like read in the noise. All right.
The depth.
The depth. What about the depth?
Well, the the orbital data is much deeper. You can see on the scale on the y-axis, and you can also see in the calculation of the planet radius is substantially different.
I think for because these are for
Okay,
four different planets.
okay, all right. My
Right,
mistake.
yeah, they're labeled.
My
This is
mistake.
a no,
Okay.
no, you're good, you're good. I took these figures from, if anyone would like to read this, I took these figures from Wynn et al. 2010. It is a fantastic paper for going over the basics of like exoplanet transits and how different things that can affect your transit data. It's, in my opinion, very foundational. It's a very good read. So it's WINN et al. 2010. I can put that in here. There we go. All right. The next slide goes over scintillation, which is basically the fluctuations caused by refraction in air. That kind of adds a lot of noise to your ground-based observations. And generally, I think that scintillation can depend a lot on your instrument. And I encourage you to know the quirks of your instrument, know like what sort of data and what sort of catches and asterisks that it has. But generally, and this equation is also in Wynn et al. 2010, the scintillation of your measurements will depend on the diameter of your telescope. It will depend on your exposure time, your integration time. It'll depend on your observatory altitude, and it will depend on the air mass of your object. So take those things into account when you're taking ground-based data. Additionally, the enemy of every astronomer is clouds. Weather can obscure your transit entirely. It can put a stop to your exoplanet adventures very quickly if the weather gods do not favor you. This is a observation that was cut short at the Panfilosa de Serra Space Observatory in Portugal. So, you know, if you're not lucky, the clouds can get you if you're observing from the ground. All right. Are there any questions before I move on and start talking about strange exoplanets and how that factors into their data? Are there any questions? And don't be shy. There are no stupid questions. All right. Well, I've explained everything perfectly then. If there are no questions, I will continue on to talking about some strange exoplanets. This is a warm-up for part 4 of this talk, which will be hidden for now. But a couple of weird exoplanets to warm up with, just to show you the diversity of exoplanets that exist in the universe. The reason that I did not label this one as its test object of interest was I don't think it has a TOI ID yet. The discovery paper for this one was last year. It was 2024. And TIC 241249530b is a very eccentric and retrograde I'm going to call this a hot Jupiter. That is 5 times the mass of Jupiter. It has an eccentricity of 0.94 and is retrograde. I love planets like this because there are many different theories about how hot Jupiters can arise, like how did they become the way that they are if they didn't form very close to their stars. And there are many hypotheses about, well, did they migrate? How did they migrate? And planets like this can help tell us about how these planets could have migrated if that is what they did. I've got a video here. this is what the orbit actually looks like. It's really close and then slingshots away. And all of this it reaches out to about like 1 AU, and then it comes back and it just catches fire and then leaves. So you may be wondering, does this show up in data at all? How did they know its eccentricity? So if you look at a transit of this planet, I think that you can model for eccentricity in a transit model, but it's not screaming at you, this planet is eccentric. Like if you just showed me this data and said it's for a planet, how eccentric is it? I don't know if I'd be able to tell you just by looking at this with my own eyeballs. If we switch to radial velocity though, which usually for a non-eccentric normal planet looks like a sine wave, this is screaming at you, this is eccentric. So, which is why it's important and very, very beneficial to look at planets with multiple measurement methods. So combining transit and radial velocity measurements, this is one of the many benefits of looking at a planet in multiple ways. Another very cool planet, this is my problem child baby, I love this one, is WASP-12b, which is actively decaying. It is losing its atmosphere to atmospheric escape, and the orbit is slowly getting shorter and shorter, which means that it is expected to crash into its star within 3 million years. So this isn't like individual transit data that I'm showing you, but it is timing deviations over time of many, many different transits or occultations of WASP-12b. And basically what people have done in the past is that they have modeled the data for either precession or orbital decay. And statistical tests have found that orbital decay is far more likely in this case, which is exciting that we can see this. All right, this is my favorite part of the talk. This is the interactive part. I am going to show you weird data with nothing but like the telescope or like observatory or satellite that it came from, and pretty much nothing else. Maybe like a hint or two to help you. But other than that, I am going to have people guess what is causing these strange phenomena that arises in this data. The solution could be something that I've talked about, or it could be something entirely different. I want you guys to use your creativity and your imaginations. There are no dumb answers. I want to hear all of your fun brainstorming. I want to hear it. Are there any questions before we begin? Oh, I see in chat. Wouldn't the planet's velocity in separated? It's moving. Oh yeah, for the WASP-12b paper, I will refer you to Turner et al. 2021. That basically goes very much in depth into these measurements that they did and comparing with previous data as well. For the sake of time, I will refer you to that paper, and then we can chat after the talk if we have time. Are there any questions? All right.
I've not used it before, but I will try to see if we can do a poll, which will help the answering. See if that
Ooh,
works.
we could do that.
Yeah. Go ahead.
All right. Without further ado, Weird Data, the game show. We've got the first one. What's going on here? What does this data look like to you?
Are these solar flares?
Are they solar flares? I'm going to write down people's answers. Solar flares. A barrage of solar flares.
Could it be many sunspots?
Sunspots. Many sunspots. Anything else? Anyone else confident about their answers? Sunspot. We've got a split. Half says solar flares, half says sunspots. Big planet that's leaving a cloud of dust behind. Solar flares. Anything else? All right. Put down your pens in 3, 2, 1. Couple of sunspots that rotated around. Maybe, maybe. Feel like we've got a 50-50 split for solar flares and sunspots. Let's see. The answer is sunspots. So this is HAP P11b. It is a planet that is moving over sunspots as it transits, with a twist. So basically, people have found that it orbits perpendicular to the stellar rotational plane. So it is orbiting from pole to pole across its star. And you may be wondering, well, how did they do this? How did they find this out? Part of the way that they did it was that if you sort of fold and stack every transit on top of each other and take residuals of each transit, so you're just left with residuals. So you can see kind of where the sunspots are in the transit as the planet moves across each time. These sunspots appear in certain parts of the transit consistently. And it's not just 2 long-term sunspots. The paper that this was published in found multiple separate sunspots across, I want to say, 26 different transits. So they were all individually identifiable sunspots, but all in around the same places. And basically, if you know anything about sunspots, you're probably familiar with this diagram. It is the sort of sunspot butterfly diagram, I like to call it. It's basically a plot over time of sunspots and their latitudes on the sun. So basically, sunspots can wax and wane, but generally they go from a little bit above and below the equator to 30 degrees north and 30 degrees south. So, and if the planet were going pole to pole, that is exactly where we would see sunspots. So yeah, this is sunspots, but with a fun twist. Are sunspots an indication of the health of the star or just a regular occurrence? To my knowledge, they're a regular occurrence. Like our sun goes through a solar cycle every 11 years, where the sun will not have basically any sunspots, and then it'll climb, and then it'll get loads of sunspots, and then go back down again. So sunspots are a regular occurrence. Sunspots are caused by fluctuations in a star's magnetic field. That is my understanding of it. Thank you for your question. All right, next transit. What is going on here? We have a lopsided asymmetrical transit, and the only hints that I'm giving you are it's from TESS, so this is space-based, so no atmosphere, and then A-type star. That's it. I want to hear your fun ideas. What are your fun ideas?
I think it might be like a binary system
Binary system. Do tell. Why do you think that?
because I think that an A-type star wouldn't really have that many solar flares as much as like an M dwarf. And also like the fact that the dip is very like regular, it's not like a spike. It's very smooth. So
I see.
and A-type stars are like, it could be that it has a binary pair, maybe like a smaller pair.
I see. I'm writing down people's answers. Binary, pair. Something went wrong. I love that. Something is deeply wrong. We have eccentric orbit. Planet is getting further away and causing a smaller dip. Ooh, good thinking. Good thinking. Anyone else want to take a stab at this? Fast rotating star. Do tell. Do tell. Anyone else? There's a fixed sunspot, but the star is moving very fast. It may cause that graph. Good thinking. Good thinking. Yeah, when I first saw this plot, I'm like, is this like an egg-shaped planet? What's going on here? Uh, so yeah, I want to hear all of your thoughts. I want to hear every one of your thoughts. All right. CCV and it's a dust plume. Dust plume. All right. Drop your pens in 3, 2, 1. So this one was not at all obvious. Someone did get fast rotating star. I am very, very, very happy about that. This is because the star is a fast rotator, but maybe not in the way that you would expect. So Kelt 9 is a rapid rotator at its surface, which induces it induces two effects. First, the star is not a perfect sphere. It flattens into an oblate shape. So because of there's like high centrifugal forces near its equator. What this causes is that the star's surface gravity decreases near the equator, resulting in an effective temperature gradient, which varies between the hot poles and the cooler equator. So basically, fast rotator, gravity is weaker at the equator because of that. And then the temperature gradient caused by that causes a sort of luminosity gradient. So, and on top of that, just to throw it in there, this planet is orbiting from pole to pole, and also the observation geometry for this star planet system is extremely strange. So that is kind of what's causing it. If you're going over the hot, more luminous pole, and then you're blocking some of that, it's going to cause a larger dip than if you were covering some of that colder, less luminous equator. And remember, it doesn't even have to be that much of a luminosity gradient, because these measurements are very, very precise. They're going into the small digits. So it doesn't take a lot. And I also just really wanted the opportunity to talk about Kelt 9b, because oh my goodness, this thing. So Kelt 9b is a ultra hot Jupiter orbiting an A-type star. So not only is it burning up, it's really close to its star, it's orbiting a blue giant star. It's the equilibrium temperature of the planet is 4,600 Kelvin. That is hotter than the average temperatures of K and M stars. So this planet is hotter than most stars in the universe. I cannot even begin to imagine the chemistry that has to be going on in this planet's atmosphere. Which it's rapidly losing. This thing is rapidly losing its atmosphere. Just to give you an idea of how extreme this planet is, this is a unfinished plot that I was making for a proposal once. And basically on the y-axis, we have solar insolation normalized, which basically is a measure of, okay, like how cooked are you? How cooked is your planet based on how luminous your star is and how close you are to the star itself. How cooked are you? And on the x-axis, I have the escape velocity, which is basically a measure of, okay, how well can you keep your atmosphere? How large are you? How much gravity do you have? How good are you at holding on to your atmospheric molecules? And when I was making this plot, I was like, oh no, there's got to be a typo. There's no way that that could be real. Did someone like add an extra couple of zeros to a planet and that's why there's this massive dot that's just ruining the plot? No, that's real. That's Kelt 9b. That's a real planet. Um, so yeah, this this friggin' thing is the reason that all exoplanet plots involving temperature or insolation need to be made in log scale. It's because of this thing. So more people need to know about this planet. I love it. I love it very much. All right, what's going on here? This is the Very Large Telescope in Chile. So it's ground-based. What's wrong with it? What's going on? Very funky looking.
Does it maybe have like multiple orbiting planets or bodies?
Multiple orbiting planets. I've got a question for you. If it's multiple orbiting planets, then how many planets? Can you count them?
Perhaps one, like three, or
3.
one, or two. Wait, no, I think three. Yeah, it's a
You
little
think
hard
3?
to. Yeah.
Betting on 3. I've written that down.
Okay.
You'll get marks on the quiz.
Okay.
I'm kidding. Are there any other guesses as to the nature of this data? The prize for guessing correctly is praise. All right. Yeah, so basically 3, 2, 1. This was a figure from the original TRAPPIST-1 discovery paper. So this is TRAPPIST-1 C, E, and F transiting at the same time. You see this large initial dip because 2 planets are transiting the star at the same time. And they all leave at different times. So you were correct. You were correct that there were 3. So for those not in the know, TRAPPIST-1 is a very interesting system. It has 7 planets, all rocky, orbiting a M-dwarf star, 3 of which are in the habitable zone. So this system is very exciting for orbital resonance people and astrobiologists. This star is very notoriously cranky though, as terms of solar flares. So like that's the reason why people, even though this system is extremely exciting, people are still trying to figure out whether or not these planets have atmospheres because it's difficult to measure in the solar flare sense. This is a animation of what the TRAPPIST system looks like. I'm gonna let it play for a bit. Got 7 planets, and then it's gonna plot some data as the planets transit. There we go. And all of the periods for these planets are very short, so that's another great thing for opportunistic exoplanets people. Got no shortage of data. Even in this example, you can see a couple of solar flares, see a couple of spikes. So yeah, this is TRAPPIST-1. And this is over the course of 10 days, so short. And this is enlarged 25 times compared to our own solar system. So because the M-dwarf star is very, very cool compared to our own sun, all of the planets can be huddled in right close to the star, and 3 of them can still be in the habitable zone. All of these planets are well within the orbit of Mercury. All right, next one. What's going on here? What's going on here? We have multiple different transits, all of various shapes and sizes. In chat or just unmute your mic.
I guess this system has many planets also.
Many planets also. Across the edge or center of the star. Good observation. What's the shape of these transits like? Because there's multiple transits. They've got interesting shapes.
I would say the red one is the one where it's like right across the outer edge of the star. So it's fast, it's deep, and then it's back up again very quickly. So it's short. Or it's either, or it could be a very close uh, companion.
Binary star companion while the others are planets. Also a good guess. Shape of the graphs being parabola to be an indicator. Yeah, so take a look at the shape. I did not go over this, but I will go over this soon. Shape can be important.
Yellow one looks like a normal transit.
All right, put down your pens in 3, 2, 1. So yeah, this is Kepler 16b, or the Kepler 16 system. So as you can see in this diagram, there are 2 stars and 1 planet. So there's star B eclipses star A. So this first one is an eclipsing binary. Star A occults star B, and then planet B transits star A, and then planet B transits star B. So the shape of your transit can kind of help you figure out what you're looking at. If you have a sort of V-shaped transit, it can either be indicative of like your planet is scraping the top of your star, which I think somebody mentioned, or it's an eclipsing binary. And occultations can be tricky. So the actual geometry of this system looks like this. This is a circumbinary planet. Kepler 16 capital A is a K-type star, and Kepler 16 capital B is an M dwarf. And they're on the outside of this little dance in here. There's the mini Saturn gas giant planet that is Kepler 16b. One of my favorite things to tell people is that Tatooine exists, it's real, and it's called Kepler 16b. Even though Kepler 16b isn't rocky, it's a mini Saturn, but still, this is the idea. This exists. In fact, I believe that there are now like at least a dozen circumbinary planets known. But this was the first one that was discovered and widely accepted. All right. This is the last one. This is the last guess that I'm going to give to you guys. What is going on here? This looks very, very strange. What is this? At the top, we have dip 5, and then on the top right, there's dips 7 through 10, and I think the ones on the bottom are zoomed in versions of the top right. What on earth is going on here? It's flux in time, but it looks really, really strange. Does anyone want to take a stab at it?
I mean, this might just be a wild guess, but maybe a planet is like being like broken up or something.
Broken up, broken up. Yeah, there's a lot going on here. There's a lot.
Yeah.
You can also take a look at the y-axis for these plots because like transit depths are typically, 0.999 depth. This is really deep. These are really deep. What's going on here? Shattering into many pieces. Yeah.
Is
Broken
this
up.
Tabby's star?
This is Tabby Star. I was really mean by putting this in here. I was being really, really mean. This is Tabby Star. And the answer to what's going on here is that nobody knows. Nobody knows the answers to what's going on here. So Tabby Star was discovered by the Zooniverse Project Planet Hunters, and it was just aliens. It's due to aliens, guys. Actually, hold on. I'm gonna skip a slide. It's gonna be really funny. So it was discovered by the Planet Hunters, and they had no idea what they were looking at, and it was just like this really, really strange star, and no one knew why it dipped like in 15-20% at seemingly almost periodic, but kind of weirdly random intervals. It was really weird. In fact, for fun, I went to like the Wikipedia page for Tabby Star just to gather like all of the proposed uh solutions to the Tabby Star problem. And as I was scrolling down the Wikipedia article, it was just getting increasingly more either specific or just deranged. Artificial megastructure is on here. It could be aliens. It could be aliens. As I was making this slide, it was like reminding me of like this picture from Dante's Descent into the Inferno. However, I do have so it could be a Dyson sphere. I do have an update on Tabby Star. I do know that in 2016, a Kickstarter fundraising campaign was proposed to use the Las Cumbres Observatory Global Telescope Network to continually monitor the star. And they got the funding, and they basically looked at the star in multiple wavelengths over long periods of time. And whatever is causing this to fluctuate in wavelength rapidly, uh, it varies by wavelength. So I think this may rule out the Dyson sphere unless it's made of glass, maybe. But the most probable maybe explanation for Tabby Star would be space dust? Question mark. All right, and with the short amount of time left, I've got 5 minutes left. I am going to give you guys some parting gifts for some resources that you can use for transit observations, either ground or space-based. To look for parameters, you can either go to the Exoplanet archive, where you can look at basically the parameters that every paper on each object has published. The Exoplanet archive parameters don't always agree with each other, but it's basically a development of, okay, how are people improving their measurements? What can you use? What's available? Also, you can access ExoFOP, which has a lot of really good information about your exoplanets. Another really great site is exoplanet.eu. It's a really good place where you can find multiple published papers on whatever you're looking for, so it's really good for lit searches. ExoMast has both data and parameters, and TEPCAT is a really good site. It's basically it's like a downloadable like table filled with like all of the measurements or all of the parameters that you could ask for with no error bars, but it's like really good for making figures. So that's a good site, and it's constantly updated. Where to find space-based data? You can find data from multiple telescopes, from multiple observatories at StatSci. That's how I get a lot of my test data. To also get test data or Kepler data, you can go to AstroQuery or Lightcurve Python packages if you know a little bit of Python. I have linked here, I have a AstroQuery example to download test DVT files if you are so inclined to use a Jupyter notebook with Python. to download your data. And finally, this is where you can find ground-based observing targets if you are a ground-based observer and you want to figure out which transits that are available to you, given your location, your latitude, your observatory, the hour angle that you want your transits to be in, et cetera, et cetera. So astro.swarthmore.edu. This is a very great site. That is it. Do you have any questions? Thank you so much.
Where are you getting most of the data that you work with?
So I work pretty much with space-based data right now.
Mm-hmm.
And I am learning all of the ins and outs on how to use Lightcurve and AstroQuery. Basically, you can get multiple different types of data that way. Like for tests, there's multiple different data types, data files, FITS files, with different levels of detrending. Like you can get LC files like Lightcurve files. You can get DVT files, which have like an extra layer of detrending attached to them. But if you want to work with the more raw data and do more detrending yourself, then I would recommend downloading LC files. It kind of depends like on like what I would want, the file type that I would want. It kind of depends on like how well the DVT detrending actually worked, because for some smaller planets, the pipeline might not work as well, like the cookie cutter pipeline. So
Do
yeah,
you
these are
work
all
at
really
trying
good.
to find new candidates for study that have not had studies or are not in the test database?
Not in the test database. I do know that planets that are really good to study would be, and is this for space-based or ground-based? Because that kind of affects the answer.
Well, either one. I mean, we have a telescope to do ground-based, but we stay within the test objects that are over on Transit Finder.
Mm-hmm. Yeah, so if you wanted to look for objects with like Kepler IDs but no TESS IDs, you may want to, because like ExoFOP is a really good tool for seeing, okay, does something have a TESS object of interest ID attached to it or not? Is something like, and for some TESS objects or Kepler objects, they have loads of data attached to them, but like no one's really touched them in a long time, or things like that. But like, there's lots of little niches you can get for different data products. So yeah, I think a good place for figuring out if your planet has been looked at in a long time would be exoplanet.eu, because basically if you go to this site here, filter sort, I'm just gonna pick like a random exoplanet. I'm gonna pick this guy. So it has like parameters and things, and related publications is one of the places where you can look to see what the most recent publications are, because it's the most recent publication for this random one that I just clicked is 2012. So this one has not been studied in a while, and this is a good way of looking into what work has been done on certain planets.
What about the ones that have no work?
The ones that have no work,
Yeah.
as in ones that have not been discovered yet,
Yeah.
go out and discover them.
That's what I'm saying. Where would be a good place to kind of sniff around?
Right.
Gaia. So that raises a question.
Probably.
Gaia DR4 is supposed to be coming out soon. Are you familiar with what they're working on in that release?
I'm more I like my field of expertise is more with exoplanet characterization of like exoplanets that have already been discovered.
Okay.
But I think like exoplanet discovery, I think Gaia, it's really standard. I think that would be a good place to look. Let's see. I
had
think
heard that DR4 is going to be have a subset of catalog items that are specifically indicating likely exoplanet stars.
yeah, that's
Unstudied.
really exciting. I think Gaia would be good.
Okay.
So yeah, but these are all there's loads of catalogs out there for exoplanets either that have not been studied in a long time or need their ephemeris updated. Um, that number climbs every day, the 5,983 confirmed planets. I'm counting down the days until it reaches 6,000. I'm counting down the days. It's almost there. All right. Are there any more questions? I know it's 2:03. I know we're past the hour, but
Yes, anyone, if you want to stay, we're not limited to 1 hour.
oh, absolutely. Yeah, absolutely. If people want to like go through these links, I would be more than happy to give a demo of anything that people find interesting.
I have a question about something we talked about earlier.
Yeah, go for it.
So I remember you were mentioning something like about figuring out like the radial velocity of planets.
Mhm.
Can you tell us how would that be done with like a telescope or with what equipment is that done with?
Right. So there's a really good GIF that like describes RV measurements really well. I could like look it up right now. Um, basically, radial velocity measurements. In fact, let me do that right now. Let me find that GIF for you. Radial velocity measurements they're done using spectra, basically. My computer just froze. Hold on. All of my windows froze. There we go.
Oh, no.
Um, velocity GIF. So basically, here it is. So how radial velocity works is you're taking a spectra of the star, and if there is a planet around that star that's large enough, it could gravitationally affect the star, and it can kind of make it move. So where like the center of mass is not like completely in the dead center of the star itself. If they kind of call this like the wobble method of if a planet is gravitationally affecting a star, it can kind of wobble. Uh, so if you watch over time a spectra of a star planet system, the spectral lines of that star could be either red shifting or blue shifting, depending on if it's moving towards or away from you. If that star, because of that planet. And then from this, they can kind of calculate, well, okay, how fast is it moving forward or away from you? And that kind of creates this sine curve. You can kind of imagine that this is for like a relatively non-eccentric orbit, while what we saw earlier, I'm gonna just exit. Uh, we saw earlier this
Yeah.
this awful thing. Oh wait, can you still see my screen? I think I went to fold.
Yeah, I can see.
Okay. Um, this isn't just like, wobbling it. It's like slingshotting it. It's
Yeah.
like jerking it forward every now and then. And it's just like that's what an eccentric orbit will do. So that's how radial velocity can tell you, oh, your planet's really, really, really eccentric. So yeah, that's what it does.
Awesome.
Thank you for your question.
Yeah, thank
How
you.
do I exit full screen? Oh my goodness, how do I do anything? There we go. Are there any other questions?
Is it okay if I ask one more question then?
Of course, yes. Of course.
Okay. So yeah, I also wanted to ask, it's like slightly off topic, but I'm looking towards like applying for PhDs very soon.
Hmm.
And I wanted to ask you, how was that process like for you? Because I want to also do astronomy, astrophysics as PhD.
Right. Yeah, I'm fresh out of that hell experience because I'm like kind of like a early grad student. Can I still be called that? I maybe like early to middle, that kind of terrifies me. I'm gonna say early. I'm about to enter my third year um of grad school. So the way that I went about applying to grad school was I started pretty early in the sense of like I started applying to like scholarships or whatever to not even just like, oh, like for sure I'm gonna get these, but like to encourage me to start early and to write all of my essays early and to have something by the time I'm like entrenched in my fall classes and I'm like dying from schoolwork because then I'm just not gonna have time to apply for grad school.
Yeah.
That's like advice that I give people. Other advice is do not be afraid of cold emailing people. Lose the shame of cold emailing people because that is how the process works. You have to cold email professors and be like, I like your work. I want to work with you. In order to get the ball rolling. It is much more likely that you could get into a place if the people doing all of the applications can put a face to a name. So that part of the process is important.
Okay.
And best of luck.
Yeah,
Best of
thank you.
luck.
Would going to scientific conferences help?
I think there are a couple of conferences where historically they have done like grad schools have gone to conferences to do like quasi interviews, I think. I can't remember if they did this at like DPS or what was I thinking of? Darn, I should remember this. But I think that it can't hurt like going to a conference and networking and meeting people. I think that is always helpful. That won't ever hurt you, I think.
Great. Thank you.
Of course. I'm like I really want to give good advice for the whole grad student thing, but like the further I get from that, like the more leaves my brain and it makes me sad.
Yeah, understandable.
Like the trenches. Oh God.
Alex recently completed a binary star paper, and it's published at JDSO in July through Great Basin. Would referencing the fact that he has a paper like that be of help in getting into a program?
I mean, you could certainly put it on your resume. I think like a publication would be really cool, like to brag about. Basically you want to, because like there's also there's the research statement and the personal statement. And those are like two different things, and you're gonna want to put like, and of course, like everywhere requires like different lengths for these statements, so you're gonna have to like write or like change. But yeah, I think putting a paper like I've published this paper. This is the work that I did. These are the skills that I learned that I can apply to my grad student research. They're looking for that. They're looking for skills. They're looking for that you maybe know how to navigate the process of a publication or like how to go about it. Or like, you have to don't just like spin it like I did this. I did this thing. This is my publication. Also spin it of like I learned statistics for this. I learned how to use a ground-based telescope for this. Like milk it.
Okay.
Milk it. Milk it a lot. Everything that you learned how to, I don't know, work with other people in a group setting. Really milk that. It's good.
Awesome. Thank you very much.
Of course. Thank you very much for participating and watching my talk.
Yeah, of course. It was really fun.
Thank you. All right. If there are no other questions, are there any other questions? All right, then. Thank you all so much for attending. I've had a blast. I hope that you have all had a blast. This is very fun. Thank you very much.
I think a round of applause is warranted. So unmute yourself or raise your hand.
Yeah.
Really well done. I really
Yes.
enjoyed it, Skylar.
Yes.
It's great to
Thank
see you again,
you.
Skylar.
Yeah.
It's good to see you, Jerry. Thank you for coming.
Okay, like I said in the chat, if you want to get a recording or get a link to the recording for this for a presentation, just email briefprograms@gmail.com.
Oh yeah, and I can put my own email in chat if
Yes,
people
if you want to
would
share
like to
your email,
contact
that's
me.
great.
If you have any questions about exoplanets or working with data or getting into grad school, honestly, like the hell process that is, contact me.
Okay, thank you very much, Skylar. This was really well done. I really, really appreciate it.
Thank you so much for having me on. That
Oh,
I would not be in this position without Boyce-Astro. Putting that on record. It is true.
thank you. And hope to see you again sometime soon on Zoom or elsewhere. So we'll
Of course.
okay. Well, thank you again. Thank you very much.
Thank you
Goodbye,
so
everyone.
much.
Thanks,
Have a
Pat.
wonderful
Bye.
rest of your weekend.
Yes.
Yes.